force equals mass times acceleration. So that's the force of acceleration, this is the force of friction, we'll call it. So that's what this investigation is kind of looking at. Yeah. So going back up to the question, it's show that the maximum amplitude of oscillation for which the mass will not slip, which means, so the mass is not slipping in this case, that means we're dealing with a MA that must be less than mu mg. Okay, so let's just write that as our sort of a semi-equation, if you like, because we're after the maximum, so we can say it can't be greater than MA. So mu mg must be greater than, we could just write it as equals because we're talking about that condition when it is right at the limit. So we can write that as equals ma, and where a is the actual acceleration. So you can straight away see that the small m is going to cancel in this little equation, but that's not going to take us to this which we're aiming for. So we're just going to hold off on that for a few moments and continue on. So where do we go from here? Well, we know that because this is simple harmonic motion, remember, SHM, so it might be useful to look at the maximum, we've got the maximum amplitude of oscillation here, A. We can use that to find the maximum acceleration from the simple harmonic motion, which, if you remember, there's the acceleration maximum is we'll write A max is A, which is the amplitude, times omega squared, and it's on the opposite direction to the displacement. And previously you would see this equation with the modifier sine omega t, but we're not interested in that part because we're only interested in the maximum, so that's useful to us. It's also useful to look at the restoring force which produces this acceleration. So the maximum restoring force is going to be from our F equals kx. Let's just write that, F equals kx. Our restoring force is going to be F equals 2kx. So we'll just write times 2 so then our equations match, and that's because we have the two springs, and the spring constants effectively add in series, and that's because when you add them in series, as you move the mass one way or the other, you're having to work against both springs, so it takes twice the force. One assumption, I'm not sure if it's mentioned earlier, is that the spring constant is the same for both. Springs. So another little part, because there's lots of aspects of this, is that the force is also equal to, this is the maximum force beyond which they'll slip, which means you're accelerating both of those masses, the big M and the little m, so it's going to be big M plus little m times by A, and that's going to also give you an expression for the force. Okay, so I think we've got enough different expressions for the force to be able to write a bit of an equation. So let's just see if we can, there's one thing we can do prior to that, is that we know that the extension is actually equal to A, so we can put A in place there. That's going to be helpful. And if we remember that this acceleration down the bottom here, that's going to be the max acceleration. So that helps us link up quite a number of things. So we're going to put a few of these things together and just see what comes out with it. So first of all, this force, which is the force of the spring, is equal to the force being used to accelerate the two masses. So let's equate them and see what that gives us. That'll give us 2ka equals m plus m times A, because remember that small a is A max. I better write that in there just to be safe so I don't forget. That's not, I've run out of space on the edge of my screen, but anyway, so it's going to be helpful for us to have that A max part by itself, because let's just go back and see where we're aiming for. Because there's no acceleration in this expression, we're dealing with just the masses, the spring constants, and our coefficient, and g, which is acceleration due to gravity. So we're just going to cruise on over here. Oh, there we go, that's why it's useful, because this is our A max again, appears here, and we can substitute in for that. Remember, the m's are going to cancel, and we'll be left with A equals mu g. So let's go back over here, see what we come up with. So we have A max is going to be equal to 2 times the spring constant times the maximum amplitude divided by m plus m. Okay. So somewhere now we need to get rid of our capital A amplitude, because it doesn't appear in our equation over here. So we want to get rid of the capital A, and we also want to draw, well, we don't need to draw the mu g because that's already in that part of it, but we can get rid of the capital A by dealing with omega. So remember, A max is also A omega squared. Sorry, A max, the amplitude max, that is, capital A max, is also equal to A omega squared. That's this part up here. In fact, yeah, never mind that. It's going to be easier if we substitute this in for A max, and then we can cancel out the A's, and we've got omega squared, and we will be able to do something with that, which you'll see shortly. So A omega squared equals 2ka over big M, oops, just 2 peaks on that big M, plus little m. So cancel those out, and we get omega squared equals 2k over m plus m. And we know that from our little equation, there's a lot of equations here, so you're really going to have to go through and check this out, but from this equation here, mu times g equals mu mg equals m times a. So remember that A max is also omega A omega squared. So we can we can then use that part to substitute in for that omega squared. So we can take our, let's see, I'm running out of colours because I'm using so many, but we can take this here, okay, so that's the 2k over m plus m, and substitute that in for the omega squared part over here. Whoops, I've drawn my arrow in the wrong place. Over here. So let's just write that down in a little bit clearer. We've got mu mg, well, we don't really need the capital M anymore. We'll just stick with mu g. So mu g equals, going back up to have a quick look, was just our A omega squared. So so that's going to be equals A times this part of omega squared over here, which is just the, okay, that's awkward, A times by 2k over m plus m. Let's just make sure I haven't left any parts out. No, okay. So very rapidly we're going to rearrange this to give us A by itself equals mu times g times by, this is going to flip upside down when it comes over to the other side, so it's going to be m plus m over 2k. So that gives us our maximum amplitude before which it won't slip, so which is what we're after. Okay, you sort of lose sight of that sometimes when you're following all these things through. So and that's exactly what we ended up with here, which is nice. So let me just run you through all of that again, because there's a lot of steps in between. We've got this initial condition where the accelerating the force to accelerate the mass, the small mass, has to be less than the normal force, which is this part, which is modified by the coefficient of static friction. If it's greater than that, it'll make it slide, so it has to be that. So we came up with this equation above for that, and we can cancel out the m's, and that mu g part stays, the mu g part here, that stays there because it's useful, and we substitute in a omega squared as the maximum acceleration from simple harmonic motion equation. We have then found an expression for omega squared by looking at the force used to compress the springs, or compress and extend, and using that with the force used to accelerate both of the masses, because that's what is going on in both of those. The spring is compressing both the masses, and this is the springs are then, that same force is being used to accelerate both of the masses. So we've rearranged down to get an expression for omega squared. We've substituted